Priya Natarajan is an assistant professor in both astronomy and physics here at Yale. She got her bachelor's from MIT and her doctorate from Cambridge University in the UK. And her specialty is hunting dark matter. Now, when I heard dark matter, I thought it was that stuff that was in my refrigerator. But she's going to talk specifically about the dark matter that's in galaxies. And she's talked about this worldwide. And she has so many significant achievements at such a young age as well. So I'm very excited to learn about dark matter, and so perhaps you can join me in welcoming Dr. Natarajan, who's going to talk to us a little bit about it. Thank you.
Thanks so much for that very generous introduction. And it's a real pleasure and privilege to be able to talk to all of you today. And I'm really glad you're here despite the rain. What I want to talk about is a very, very important enterprise in astrophysics, astronomy, and cosmology today, which is trying to understand the contents of the universe. And it turns out that current observational data suggests that much of the universe, more than 90% of it in terms of matter, is in fact dark. And it's dark because we don't know what it is. We do not know its composition. What we do know is that it has gravity, that it exerts the force of gravity, it exerts an attractive force on objects that are nearby. And we know that there's copious amounts of it everywhere, including our own galaxy, and that it is very, very crucial. You might wonder, I mean, okay, well, we don't know what it is. Fine, let's just move on. We can't. Why? Because the fate of our universe is crucially determined by the contents of the universe. And I hope to lead you through some of sort of the basic tenets in cosmology, all of which are observationally supported, that will help you understand why the quest for dark matter is such an important and crucial exercise for cosmology today. So I start off, as I said, by giving you a little bit of an introduction, trying to sort of lay the land of what is it that we try to do when we do cosmology. Because what we want to do is to characterize the properties of the universe. We want to understand its size, its contents, its structure, obviously how it formed, how it's evolving, and how it's going to end. And dark matter plays a very, very crucial role in determining the story, the entire story. And it's very important from the very beginning. And as I said, one of the crucial things about our lack of knowledge at the moment is the fact that we do not know if dark matter is charged. We have no idea, okay? And as all of you who've done sort of, have felt static when you take your clothes off in winter, that's a very fundamental property. So we really don't know what dark matter is made of. However, we've made very, very important strides, as I hope to lead you through, to show you some of the most beautiful pieces of data that the Hubble Space Telescope has ever taken. And the Hubble Space Telescope has been very, very important in transforming this field, as I'll show you. So as I said, we first start off with some preliminaries, which I'll try and explain to you what the basic properties of the universe are. And some of my motivation in doing this is I want to also sort of pique your curiosity, so you'll all go back home, go into Google or something, and start searching for some of these things and learn more. So I'm going to give you just a very sparse introduction because I want to lead you right into the quest for dark matter and hope to lead you through sort of this journey in a historical fashion, the way it has happened in cosmology. So some of the important properties of the universe that we need to understand and sort of keep track of are that it's static, right? This was the idea that people had before we had any observations of the motions of galaxies. So what I'm planning to do is to try and show you that these are the ideas and how, as part of science, some of the older ideas get replaced by the newer and current ideas as we gather more and more data. So in the 1700s and 1800s, people thought there was no motion. I mean, the universe was static. There was no motion. It was infinite, and it had to be infinite to balance all the matter. Of course, at that point, they also realized they did not know there was dark matter in the 1800s, right? So they knew there was a solar system, there were other planets, and possibly other stars and other nebulae, which were other galaxies. Then it occurred to them that, oh, well, a finite universe has to have an edge. I'm just trying to motivate the idea of gravity here. So, why gravity, even on the scale of the universe, is so important. So material at the edge of the universe would clearly feel, if there was an edge, would feel the inward pull of gravity, and it would start moving in. However, they never saw any motion, so they said there can't be an edge, so the universe must be infinite, right? But there are lots of problems with an infinite universe, and some of those will become clearer as we move along. So for example, this is a question that I want you to think about, and I would be happy to have volunteers come up with suggestions at the end of the talk as to why is the night sky dark. Okay, so there were many ideas, sophisticated and unsophisticated. The first of which was, oh, the sun set, of course, so that's why the night sky is dark. However, the fact that the night sky is dark is very crucial, has a crucial bearing on the size of the universe. Because in an infinite universe, can the night sky ever be dark? And that's something I want you to think about, and we can come back to it at the end of the talk. So in an infinite universe, of course, you'd have an infinite number of stars. There would be infinite starlight. It should be infinitely bright. That's not the case at all. So obviously, the solution is not that the universe necessarily isn't spatially infinite, but that isn't infinitely old. And this is the statement that I want you to demystify at the end of the talk. And I think you will have a very clear idea of why that is so. The obvious reason is we can't see all parts of the universe, but we can see what's nearby. So that was to give you an idea of the progression of how people thought about the size and the scale of the universe. So let's talk. So let me give you like 3 nice technical terms that are easy to remember and that are very physical. So the modern idea, what we know from current observations, is the universe is homogeneous on very large scale, i.e. material, galaxies, are fairly uniformly distributed. And you might wonder, why is this important? It's a very important, crucial mathematical property, which we will see manifest itself in a very nice way observationally. We also think that the universe is isotropic. It looks the same to all observers. This is another very tricky but neat thing about the universe, that there is no special direction, there is no special center, and we'll come to that. So these 2 properties, very simple ideas, that all the material, all the galaxies are uniformly distributed, and that there's no preferred direction in the universe, combined together, form the basis of current cosmology, and that's called the cosmological principle. And you might wonder, well, why is this such a deep principle? Obviously, one of the things I'm not showing you here are all the mathematical equations, and this is, in fact, a very crucial mathematical property. These 2 quantities are actually mathematical properties that lead you to the current observed universe. But they have a very nice physical, simple basis. So these are the basic assumptions that we are starting out with, and observations show us that those assumptions are true. The other thing you might have all wondered is that, I'm trying to persuade you that even in the universe, what was that? Oh, yes, I know. Even when I'm teaching, it often tells me, your battery is 30% charged. At least it's fully charged today. That's good. So the other thing you might wonder is I'm talking to you about gravity, and you might think, it's true, an apple falls, and it falls down to the earth because of gravity. But, do these laws have to hold everywhere in the universe? In fact, as physicists, the assumption that we make is that all these laws, universal laws, actually hold everywhere in the universe. And that's very crucial, because you can imagine that you won't get very far if you think that on the Andromeda galaxy, gravity doesn't work, and it's a completely different set of laws. Because we wouldn't really be able to make any sense of our observations if we don't make this assumption to start with. And of course, we can test these assumptions, which we do. And this one holds out pretty well, as we'll see. Okay, I don't know why it's not moving.
You clicked out the program, you had to click on it.
Pardon?
You clicked out the program and you clicked on that text box.
Oh, did I do that? Okay. So now the current models of the universe try to produce a universe that follows this cosmological principle. and the principle of universality. Okay? So all the models, all the mathematical models that we're going to try and test have these properties to start with. The question is, as I keep repeating, that the observations are the final test, right? So these are the assumptions that you start with, but the question is whether the observations hold up. So what I want to show here is one other very, very crucial property of the universe that is a bit tricky to understand, but is very, very crucial. Okay? So you might have all heard that the universe started 14 billion years ago with a Big Bang. So the natural idea that we have in our head of a Big Bang was, sort of like a bomb, like an explosion that happened in one particular location. So that analogy doesn't quite work, because the Big Bang happened everywhere. It didn't happen in a special place, because whatever space was there when the Big Bang happened was everywhere at that time. Okay, so that's a slightly difficult concept. But basically, the idea is that there is no single center to the universe. There is no special place in the universe. Okay, every point in the universe is equivalent. So you can call any point the center, any and every point the center of the universe. And you might wonder, yeah?
What about the galactic hub?
What do you mean by the galactic hub?
I heard about this place where there's a bunch of galaxies that are grouped together.
Yeah, there are galaxies that group together by gravity, but that doesn't mean that's the center of the universe. So let me just try to explain why there is no center of the universe. So one of the observations that is made is that you see galaxies around us receding away from us. Okay? And what that means is that the universe is in fact expanding. Okay? If there was a preferred center to the universe, all galaxies would be receding only from that particular place. Now, if we move a spectrograph to the Andromeda galaxy, which is the galaxy nearest to us, you in fact find that with respect to the Andromeda galaxy, everybody else is receding away too. So the concept of having one center from which everything is flowing away just doesn't work at all. So that is the sort of incontrovertible proof that the universe itself is expanding, which means there is no special center. And I think the easiest way to think about this is to think of the universe basically as a piece of fabric. Okay? And we are all galaxies, we're all embedded in this fabric. And in fact, rather than these galaxies moving away from each other or from a center, what's really happening is the fabric itself is expanding. Okay? So that's what's really happening. So this fabric is in fact technically also called the space-time fabric. Okay? So it's just a sheet. You can think of it as a sheet. And the sheet analogy works really well because the presence of mass in the universe causes little bumps in this sheet. So think of a sheet. Think of a bed sheet or something, and you drop an apple into it, and you form a little bump. Right? If you hold it taut from the sides, you make a little bump. That's really, that's the best analogy that you can make to galaxies in the universe. You basically have this sheet that's stretched, and that's in fact stretching and expanding, as I just told you. And all the galaxies and other objects in the universe are causing little bumps in this sheet. They are not keeping the sheet straight. Okay? They're causing little sort of bumps as we go along. And those bumps are going to be very, very crucial because those bumps define the geometry of the universe. How bumpy the space-time is tells you something about the shape of the universe, the future of the universe, as well as the geometry of the universe, as we'll see. Now you might ask, okay, great, I understand we're expanding, the sheet is expanding. Are we expanding into something? No, we're not, because I've told you the universe itself is this sheet. So we're not expanding into anything else. Space-time itself is expanding. So these are slightly tricky concepts, but I thought that you might wonder, oh, is this going to mean that we're going to have many more parking spaces? Something of relevance today, right? You want to park as close as possible. But alas. Now, this is where we come back. So what are the concepts that I've just told you about? This idea of the universe being a sheet is one of the major achievements of Einstein's general relativity. And in fact, it was this concept that he developed, which has been the backbone of all of cosmology and fundamental to understanding the structure of the universe. So this idea that the universe can be thought of, space-time can be thought of as a sheet in which the presence of galaxies cause little bumps is a major insight that Einstein had. And I'll just show you, when we map dark matter in the universe, it's very crucial to have this picture right. Because remember, if you're trying to map, if I'm trying to map, do a cartography on New Haven or something, it's very, very important to know the definition of terra firma. Okay, what is the soil? What is ground? What am I mapping stuff on, right? So it's very important to know whether there is a ground and there are objects on the ground if I'm going to do cartography. Similarly, in the universe, if I'm going to map dark matter, I really need to know where the hills and the valleys are and what's going on, right? And so general relativity tells you that the structure of the universe is such that the presence of masses cause little bumps in this sheet. And the one other thing, I don't know if you caught me when I said that we want to think of the universe as space-time. And we wonder, why did she mix up space and time? Because actually in our universe, space and time are very intricately linked. So in order to specify an event in the universe, you have to specify not only where it happened, but when it happened. Okay? Unlike for us, we can specify, we can say, well, I drove in from Hamden. And sure, if we need to figure out how long it's going to take to drive from there, we need to specify the time. But we can uniquely describe events in our daily lives by just talking about either when they happen or where they happen. We don't necessarily have to put them together. In the universe, you cannot describe an event uniquely unless you say when it happened and where it happened. Anyone has any ideas as to why it's important to specify when something happened in the universe? Yep?
Because two events that are different could have happened at the same place at different times.
Absolutely, absolutely. I think she's hit a very, very important point, which leads on to the fact that one of the reasons we need to do that is the speed of light is finite. Okay? Light travels at a finite speed. And it's something that we don't experience in our daily life. I mean, we might have noticed that it takes 8 minutes for light that's emitted from the sun to reach us. But it's not something we experience, right? I mean, 8 minutes is not that long. However, if you think of the sun is the closest star to us. However, if you think of all the galaxies that we're going to be seeing in a little while, that are hundreds of millions of light years away from us, it takes light a finite time to reach us from those galaxies. So in fact, we see those galaxies in their youth. We don't see them as they are today. We see them as they were 100 million years ago when light left those galaxies. Now, this would be really nice, right? I mean, if this was of consequence to us, you would be seeing not me, but a picture of me when I was an infant right now, right? Unfortunately for us, it's not relevant for only because the speed of light for anything that has to do with our day-to-day activities is practically, it's very fast. You pick up the phone, your signals work immediately, right? There's no delay. Whereas when we are talking about astronomical objects, the fact that the speed of light is finite is consequential. So what do we know now about the universe? So this is the starting point before we start mapping, probing the universe. We think that the universe is uniformly expanding, okay? And this law, where I said objects nearby to us are receding away from us, was discovered by this astronomer, Edwin Hubble. So it's named after him. It's called the Hubble law. And if the universe were not expanding uniformly and sort of doing it sort of kinkily, different places have different expansion speeds, then you would not be seeing, as I said, the galaxies around us uniformly going away from us, right? Some would be coming towards us, some would be going away. In fact, we don't see that. For those of you who want to whet your appetite with a little bit of mathematics, the only equation I have here today, but something that's very simple and you would want to know this, remember I told you that these objects are receding with a particular velocity. So that's a speed, so that's a distance traveled per unit time, and that is proportional to the distance from us. So the objects that are closest to us are receding not as fast as the objects that are further away from us. Okay? And that this little h0 that you see here is what Hubble found as a constant. This is why it's called Hubble's law. This number is called Hubble's constant. And you might say, why is she telling us about this number? The interesting thing about our current universe is that you need to specify 6 numbers, just 6 numbers, to tell you everything about the universe. The content of the universe, the geometry of the universe, the fate of the universe, the end, the start, everything. Okay? And this is one of the important numbers that characterizes our universe. One can think if there was another universe, there are theories that suggest that there might be other universes from which we don't have enough time for light to have traveled to us to tell us anything about them, but they could potentially exist. And this number would be very different for a different universe. For our universe, this number is about 65. And you might say, why is 65 special? It's not particularly special. That's what we measure. Okay, so this is a number that we go out and try to measure as cosmologists. As I said, the objects that are farther away from us move much faster. That's just a restatement of this mathematical law. And you might say, that just suggests, let's go back. That's going to suggest that we're at the center of the universe, right? But we're not. As I said, the reason being that you could make the same measurement from another galaxy and you see the same law. Okay? And you might say, how do you make the same measurement from the other galaxy? Well, you get light from different galaxies, and the light from different galaxies have different characteristics, and we can therefore separate out the bit that has to do with the motions of the galaxies, which we now do routinely. And we find that this Hubble law is valid from the perspective of the little person who is living on Andromeda. So clearly, there is no center to the universe. Okay? So one other sort of crucial fact we want to know before we start mapping the universe and looking for dark matter is understanding that space has curvature. Remember the sheet that I told you about? In fact, it's not a flat sheet. I already told you that it has little bumps. The question is, in and of itself, does it have any shape to start with? How is it stretched? And the space is really synonymous with what we call our universe. It's being stretched by the expansion because it's being pulled, right? And it's being uniformly pulled from all sides. And how much it is pulled depends on whether the sheet, yeah? Do you have a question?
No,
oh, you were just stretching your arm. Okay. So it depends. How much you're stretching depends on how flat you are to start with, right? So if you have a completely flat sheet, you have no shape to it. It's just a flat sheet. It's very boring. Okay. So this is just a visualization of that. So if our little sheet, which is our universe, was completely flat, this is what it would look like, flat, okay? And the interesting thing is, triangles drawn on such a sheet, the sum of the angles add up to? Exactly. Okay, so all the properties that you know and work, on our piece of paper when we're doing the calculations in school, they work. But that's a boring description for the whole universe, okay? So our patch of the universe, where we live, looks pretty much flat because we know our angles add up to 180 degrees, right? So the piece of the universe that we live in looks locally flat. And you might say, that's a bit confusing. It's actually very simple. Just think about it. When you're driving from here to the Peabody Museum, it doesn't matter if the Earth is round or flat or whatever. However, if you're sailing from here to Australia, it's important. Right? It's absolutely important. So that's what's happening in the universe. We live on a very small patch of the universe, and the patch that we live in might as well be flat. But it doesn't mean that it's flat overall. Okay, so let's see what interesting shapes the universe might have. You might be saying, why is she talking about the shape of it? Remember, I keep telling you that the fate of the universe is determined by its geometry and its contents. Okay, so that's where we're going. Now, if it had positive curvature, then the universe would be like a sphere, and the sum of the angles of a triangle would not add up to 180 degrees. Okay? If you have negative curvature, which in my opinion is the most interesting, it's mathematically the most complicated. Okay? then it would look like this. And this would be like one of those potato chips, like my favorite potato chip. Looks like that. Okay. Now, let's get our final key concepts in place. If the universe is expanding, it must have been smaller. And if we go back far enough, we reach the Big Bang. So this story, the story of how we start off with an initial condition of the Big Bang, start off with some geometry, and end up with all the galaxies that we see around us, is what we call cosmogony, which is sort of the scientific equivalent of the tales that every culture, every religion has had to make sense of the universe. Except here, we have empirical data, right, for our cosmogony. So the current theory, the Big Bang theory, there were two very important people. I know they're very glum looking. I chose these pictures because they were so serious looking, and I thought, okay, you know what, I want everyone to see. They were serious guys, actually, and they did a lot of interesting mathematics. And I mean, the reason I think they were phenomenal was because they came up with a description of the right mathematical model for the universe well before there was any observational data. So they really had some incredible insight, okay? An insight that was not necessarily guided by data that was already sitting around. They had some enormous mathematical insight that said, okay, you know, let's try and, they weren't overwhelmed by what they had to do. They said, okay, here's the universe. Let's try and find a few equations that will describe it. And Alexander Friedman and Lemaitre did this independently. One of the reasons I chose these two people is I wanted to also point out that one of the interesting things in cosmology is that when Russia and Europe, the rest of the West, were quite separated intellectually and politically, everything happened in parallel. But you know what? They didn't exchange journals. So nobody knew what they had done, and nobody knew what these guys had done. These guys, they didn't know what each other was doing. So in fact, science-wise, it turned out to be really fruitful. You had two completely independent groups that didn't talk to each other, in fact, never wanted to talk to each other, and found the same things, and found the same formulations. So now, of course, when we give credit, we have to be really careful and make sure that we give credit to people who did it simultaneously in both systems. Okay, so now we are almost ready to go to look at dark matter. And you might say, oh, okay, so what's this fate of the universe business? So the geometry of the universe, and that's what is coded here. Remember, this is the spherical, that's the flat, and this is the Pringle. The fate of the universe from the Big Bang, that point refers to the Big Bang, and this is sometime in the future. We are somewhere here. Okay, that's today. This is cosmic time. So the fate of the universe, whether you grow, this is the size of the universe, whether you grow and keep growing, or you kind of turn over. And what does this point refer to? Do people know what this is? Crunch. Exactly, the big crunch, right? So the question is, where we are on one of these three curves determines our final fate. If we are unfortunately stuck here, then there's going to be a big crunch at some point. However, if we are luckily on one of these, things are going to keep coasting along. However, remember, none of us ever have to worry, right? Because at 14 billion years or so, we're here. So we're talking many, yep?
Most of us are familiar with the Big Bang.
Sure.
Can you just take a moment to describe what the big crunch would be like?
Sure, absolutely.
Is it the end of the world?
Yeah, the world would have ended well before then. Okay, so this, as I said, these are mathematical solutions, which are the fate of that space-time sheet, okay? So what is going to happen in this solution, which leads to the big crunch, is that space-time, instead of expanding, which it does up to a point, after a certain point, starts to contract. Okay, so it starts to contract. This sheet, instead of moving outwards uniformly, starts to contract inward. And eventually, so it starts contracting. And in terms of what would happen to galaxies and so on, galaxies would start to collide with each other, okay, much more frequently. And they would destroy each other. So at the big crunch, by the time you reach the big crunch and you approach the big crunch, i.e. when the sheet has contracted enough to become smaller and smaller, there will be no galaxies. Needless, there will be no life by then, okay? So the interesting thing about the big crunch is all the structure in the universe that you see today would be completely wiped out. So it's almost like running the movie that has happened so far backward. and you would be going back, and you would go back to a singularity, and that singularity is what we call the big crunch. And you may say, what is singularity? It would be to the point that would most resemble the Big Bang. Okay? Yeah?
Would another Big Bang happen after the Big Crunch?
It could. It absolutely could. Because then that would mean that we're living in a universe that's basically oscillating between expanding, dying, regenerating itself, and so on and so forth. Yeah, absolutely. Yep.
If we're taking one of the two paths, like any one of the two paths where the universe just keeps expanding,
Yeah.
would there be any time where it would like just separate or something?
No, we'll be on one or the other.
I know, but would there be like any end to the universe?
No, actually, they wouldn't. Well, there would be an end in the sense that at some point it might become very inefficient for galaxies to form, so no new galaxies would form. And the galaxies that are existing would just kind of age and die, okay? So you wouldn't form galaxies as fast. You would still keep forming them, but not as fast. Okay, so in some sense, that sort of universe is sort of an eternal universe. I mean, you really won't die out completely. I think there was one other question, right? Yeah.
On the middle universe,
Yeah?
after a while, it'll become, it slows down, the expanding, and in fact, the expanding goes to
Gosh.
zero as time increases, as cosmic time increases.
Absolutely.
So,
Yeah, no. So she was.
it'll get easier and easier to form galaxies. But there'll never be a push to form galaxies. It'll always try and keep from forming galaxies, but the galaxies will form much easier.
Right. So the question is, what she's trying to ask is that these two solutions, or is it a he? Sorry. What they're trying to ask is, what is the difference between these two solutions? Okay? And is it going to be that in one of the solutions, what really ends up happening is that the rate of formation of galaxies isn't really all that much affected compared to the other. So let me just explain very, very quickly what the difference between these two solutions is. So all of you are sort of familiar with the concept of acceleration, right, which is the rate of change of speed, right, of velocity. So you put the gas on, your gas pedal on, and you brake. You know what you're changing is the velocity. So what is really different about these two solutions is that one of them is accelerating, and the other one is decelerating, okay? But at a very slow rate, at such a slow rate that the one that is decelerating is never going to ultimately slow down and go to the crunch, okay? It's never going to ultimately slow down. That the expansion, yeah?
Actually, they're both accelerating. Just one is the accelerating, but one is adding the same amount of time, teenier and teenier bits in size. The other one adding also teenier and teenier bits. But one can, but flat, a flat universe could be compared to, like
Okay, why don't we talk about this? Why don't we talk about this later?
compared to a sum with a limit. That is, the partial sums go to a limit. But the hyperbolic universe could be compared to some, like the
I think there's a little bit of confusion here, which we'll talk about. Why don't we talk after? Okay. So as far as what we are concerned with at the moment, this universe, which is a flat universe, okay, is what our universe looks like if we look right around us. Okay. However, when we look further out, so what you might think is, okay, how do we figure out which solution we are sitting on? Okay. Are we sitting on the totally flat universe? Are we sitting on an open universe? Right? And an open universe can also look flat over a very small scale, although the universe itself is open and looks like the outside of the Pringle chip. However, our current universe is in fact a flat universe. Okay? And this flat universe, as I told you, although it's a little boring, It's actually mathematically the simplest in terms of the solution and the implications and so on and so forth. However, what we need to make the universe flat is matter. Okay, so we need matter in the universe to make it flat. And what the current data is telling us that our universe is flat, we need a lot of matter. Okay, and what we do is we go out there, we measure we look at the starlight from all the galaxies around us, we count up all the mass in all those stars that are giving out that light. We do a full inventory. We go and count up all the gas molecules we see in the universe, and we say, okay, how much mass is that? Is that enough mass to make the universe flat? And in fact, you find that that is not enough mass to make the universe flat. And therefore, you need some other unaccounted for mass to make the universe flat. And we need dark matter. So let's come back to why is it called dark. I mean, it's obviously called dark because we don't know anything about it. Whenever cosmologists don't know anything about something, they just say dark, whatever. Yes. So there is also no radiation. There is no light. There's no X-rays. There's no gamma rays. There's no visible light. There's nothing that's emitted by dark matter. Okay? Yep. Is doing what, sorry?
It's breathing, going in and out.
You mean it's oscillating? Yeah, those solutions are still popular in the literature, but I mean, there are people who are writing papers, but there's no observational data to support them. So he asked about these idea of oscillating universes, and a diagram for one of those universes would look like this repeating itself. Okay, and we don't, I mean, there's no evidence that the current data supports a universe like that. Okay, so now let me go on directly now. Let's move on to start mapping dark matter. So this is the dependence, the velocity dependence on radius. So the sun is here. Assume that the sun is here, and we're looking at the distance from the sun for all the planets. Okay, so all the planets are along here. And what you find is the speed with which Neptune or Pluto are going around the sun is much lower than the speed at which we are going around the sun. Okay? So that's what this plot is showing you. The closer in you are, the faster you're moving. And why is that? That is so because the closer in you are feeling the effects of the gravity of the sun much more. And you might say, okay, great, I buy that. That makes sense. Now let's see if I move this argument, if I apply the same argument to a galaxy. And I say, okay, this galaxy is the center, which is here, and there are stars. So this is, these are all, what you see here as little specks are all stars, and the stuff that you see smooth is also starlight. Okay, we're not able to, there's so many stars right here that their light looks pretty smooth, that you don't pick them up. Whereas what you see here are stars and globular clusters. So let's look at this galaxy and say, a star that is sitting right here versus a star that is sitting here versus here versus here. Let's make the analogy with the solar system. What should the motion of those stars look like? What do we expect? Okay, so let us consider. So this is just looking at the same galaxy. I've turned it upside down so we can see it much more clearly. So it's a spiral galaxy with all these arms, much like our own. And this is the center of the galaxy, and we are measuring our distance from there. We're moving out, and you say, okay, so let's look at stars at different locations and see what their speeds are like. And we can see how fast they're orbiting around the galaxy. And the thing, what turns out to be the important quantity that determines how fast they're moving, is the amount of mass that is inside their location. So if I look at a star at radius r, what is relevant is all the mass that is inside of r. Okay? That's what determines how fast the star here will be moving. So what do we expect? So we expect something like the solar system plot that I just showed you. You expect things right in the center to be moving a lot faster and then things falling off. What do we see? We don't see that. Right? We see that the speed is in fact totally the opposite of what we would imagine. It's very slow in the center, kind of picks up, it stays flat. stays flat as far as we can see. Remember, we are still mapping the stars, right? We're still looking at stars and seeing the motions of the stars. So at some point, we're running out of stars in this galaxy because, you know, it's very faint. We don't see we see sort of an edge to the galaxy, right? So this is sort of roughly the galaxy edge. But what is intriguing is that you're seeing that it's flattening off rather than falling. So let me show you some real data. So this is sort of very new data for 4 different galaxies. So these are the images of the galaxies. These are Hubble Space Telescope images. And these lines show you the slits in the direction along which you're measuring the speeds of the stars. So this is where you're getting your R's from, the various locations. Okay? So along here, you're making the measurement. What you're finding is you're starting nicely from 0, you have a little bump, and then you're flattening off. And in pretty much every case, you keep going, and you flatten off. So there doesn't seem to be an edge of the galaxy that coincides with when the stars run out. Because if there was an edge to the galaxy, you would see this plummet and fall back to 0. So something is holding up the galaxy well outside where you see stars are. Okay? Okay, so these things, I mean, for this thing to be flat, this is called a velocity curve. For this curve to be flat, you basically need large amounts of mass here, 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 here. And you know, as we're going outside to the galaxy, we know that the starlight is falling off. Stars are getting fainter and fainter. You're reaching a visible edge to the galaxy. However, the mass of the galaxy, remember it was the mass that was the crucial thing, is not falling off. Okay, so this is the very, very strong evidence for the presence of dark matter. So this is my little cartoon to show you what our current picture of galaxies is. Our current picture of a galaxy, so this is the starlight. So this is a galaxy like ours. It's a spiral. This is where all the stars are sitting. Okay, so this is the densest part where we see a lot of stars. And as we go further out, the starlight sort of oozes off, right? You see the dim starlight in that image that I showed you. And roughly here, you basically run out of stars. But then the velocity curve keeps going. It doesn't look like it's falling. It's suggestive of the fact that you have something that looks like this. You have a huge halo of dark matter that is around every galaxy. And it appears, and I showed you just 4 random galaxies. Of course, these measurements have been made for hundreds and thousands of galaxies at the moment. And you find that their rotation curves, the velocity curves, are flat. So almost all galaxies seem to have this kind of structure. They have a huge amount of dark matter. Yep?
So you can't increase your radius because you don't have a star to set the end of your ray on in order to see the motion.
Sure, but what you can do is you can, so the question, I don't know if you all heard it, the question is, of course, you're running out of stars, so can you really be sure? The interesting thing is that lots of galaxies have satellite galaxies. So often, although you've run out of the stars of this particular galaxy, you would have a little neighboring galaxy sort of sitting out here. And when you map the velocity of that guy around the big galaxy, you find that there is evidence for a continuous curve that shows you that there's a lot of dark matter. Yep?
But if what you're saying is dark matter is a halo around the galaxies, then doesn't that mean the area around the galaxies isn't a vacuum?
No, it's not. Absolutely. It's not a vacuum. And that's what is so intriguing about dark matter, because it's clearly particles of some sort, right? It's some kind of particles. We just don't know their mass. We don't know their charge. Well, we know nothing, basically. We know it exists. And we roughly know that there's a lot of it. There's a lot of it. And you might say, how did she draw this edge so clearly? And that's really what I'm going to show you next, which is the technique of gravitational lensing, which allows you to say something about how far out this whole halo of dark matter is sitting. How much dark matter do we really have? Okay, so that brings me on to the technique that we're going to use to map dark matter. And the technique is one of looking at deflection of light from sources, from objects in the universe. And this was something that was suspected by Newton and Laplace. And they said, so the picture that they had, roughly, was that you have this sort of space-time sheet. and you have galaxies that are sitting. So you think of it like, I don't know, bread with raisins or something in it. Okay, so the galaxies are little raisins or whatever. And you're getting light from all these different galaxies. We're sitting on Earth in our solar system, and we are measuring, right? We're catching all this light. We're measuring these photons. The question is, the path that these light rays take to us will depend on the geometry of the space-time between that galaxy and us. So if space-time was not flat and was like a Pringle chip, and you have two people sitting at each edge, right, and you have another person sitting in the middle at the top part of the Pringle, the time that it would take for light and the path that light would take would be a lot more curvy for the one at the corner than one at the center, right? And the question is, how can we look at the light travel time from different places in the universe and say something about the shape of the universe? Okay? And you might say, and why would the light travel times be different? The geometry is different. Okay? Why would the geometry be different? I already told you that the shape of space-time is determined by the mass blobs. All the blobs in the universe cause little bumps in space-time. Okay? Therefore, the distribution, so if I'm telling you that there's a lot of dark matter, and there are lots of dark matter blobs, they're going to affect the path of light rays. And that is precisely what Einstein figured out. He didn't know about dark matter. But what he did know, that if there's any ordinary matter, ordinary atoms, okay, and I'm distinguishing dark matter from something that's not made of ordinary atoms. Okay, we know that. We know that because if it was made of ordinary atoms, we would get some radiation, either in X-rays or gamma rays, or something. But we don't, right? So we know that dark matter is not made of ordinary atoms. But what Einstein calculated, he didn't know about dark matter, but he said, suppose there was a big clump of atoms, like another galaxy, that we just haven't seen yet, because it's faint or whatever. Would its presence be felt by this light travel time argument? And he calculated, and he found that, in fact, yes, the presence of any mass, whether it's dark matter or not, would be detectable just by looking at how much the paths of light get deflected. And you might say, yes, that sounds interesting, but let's see. So let me try and show you the observational evidence. And so I'll build up a case for how people discovered this effect of light bending by masses, okay, by the presence of mass. So in about 1979, there were these three people who went and took a spectrum and an image of a quasar, of a little patch of the sky, and they saw these two very bright images. Okay, so the a quasar, just to give you a quick idea of what it is, it's a very, very bright object. So these objects actually outshine an entire galaxy. They're very point-like. They're basically accreting black holes. Okay, they're very energetic objects in the universe. They're rare, but you do see them. So they went and they imaged this part of the sky, and they found these two objects. And they're like, oh, that's great, we found two quasars. So let's look at the characteristics. Let's look at the spectrum of the light from these two little shiny things in the universe. And let's try and figure out what they are. Okay? They suspected they were quasars, but then they said, it's very rare to find them that close, because these are rare objects. So let's see what's happening. They looked at the spectra of A and B. They were identical. Okay? So they are, in fact, two images of the same object. Because you can't have the spectra be that identical if they were different objects, because the spectra will tell you, pardon?
You can't.
No, you can't.
You can't.
No. But anyway, so what they found was the spectra were absolutely identical, and therefore they had to be two images of the same object. And you might say, how can you have two images of the same object? I don't know if any of you have done these experiments in school where you have a candle, you have a screen, and you have a lens. You have either a concave lens or a convex lens. And as you keep moving the lens between you and the candle, you see very different kinds of images of the same candle, right? Sometimes the candle looks magnified, sometimes it looks demagnified, sometimes it looks inverted, sometimes it looks as it is, right? Depending on the distance between the lens. Have you guys done this experiment in optics? simple optics in school. So much similar to that, what's happening in the universe, to make the analogy, just as you have this lens that is focusing the light from the candle to give you the image on the screen, in the universe, the thing that acts as the lens is mass, is matter. The presence of matter is what focuses and defocuses light. If you have a region of space that's a vacuum, where there is no matter at all, then you will tend to defocus the light. And every time you have a mass, you tend to focus the light, very much like the lens. The only interesting thing in the universe that's mathematically slightly different is that you might end up seeing multiple images of the same object, which you don't actually see in optics that frequently. Okay? You have to make a very elaborate arrangement in order to do that. Whereas in the universe, when things line up just so let me just now try to put all the things we've learned so far together. So this is a schematic of space-time. Okay? This black stuff, this grid is space-time. So what you have is you have us making a measurement. This is the sun. And you have a star that is behind the sun, but we can get light from it. Okay? And the position, as viewed by Earth, we see the star here. And in fact, the actual star is over here. And the reason it appears to be here is because the light has been bent, and it appears that the image of the star, in fact, appears to be here. The reason that has happened, the presence of mass, in this case, it's the sun, has caused this deflection. Okay? So this is gravitational lensing. It's gravitational because it's caused by a mass. And the mass that is doing this light bending can be as wimpy as the sun, as oomphy as a galaxy, or as extremely oomphy as many, many galaxies that are sitting close together in what is called a cluster of galaxies. All you need is some mass. And of course, you will realize immediately is how much bending you have is going to depend on how massive this lens is, how massive this object is. Okay? And of course, therefore, the range of phenomena that you're going to see, whether you see 2 images, 4 images, maybe more, it's going to depend on how massive this object is. It's also going to depend on how far we are from the lens, how far we are from the source, and what else is going to depend on? Space-time. The curvature, the shape of space-time. Okay? And the reason it's going to depend on space-time is, remember, that almost any object in the universe can act as a lens. So if the object is,
So you're saying that light doesn't always travel?
in straight lines, necessarily.
Does it?
Actually, no, it travels in
It travels in these curves that are called geodesics. Okay, that's a technical word. And that basically means that it follows the curvature of space-time. So whatever bump, pardon? Absolutely. It's the straightest path it can find, given that you have a curved geometry. So if the space-time is kind of curvy, that's the shortest path that the light can find to us. Okay? And as I said, this deflection, the extent of this deflection, depends very, very strongly on the mass of this lens. And that's what's going to be crucial. Remember, I keep saying mass. Why do I keep saying mass? Sorry, there's a question in the back. Yeah. Right. Right. As far as we are concerned, because the distance, the difference on any different 5 points on the Earth is going to be tiny compared to any of these distances, that won't be consequential. Yeah. Yeah.
When you're actually taking those measurements,
Yeah.
how do you compensate for the refraction of light? You know, the light going past the outer atmosphere of the sun is actually being refracted by the gas.
Sure. So what you do is you make a measurement of the total light within a fixed aperture. Okay, and you have ways. We have ways to calculate how much of the light has leaked out into this diffraction pattern. So nowadays, the optics on telescopes are so sophisticated that all of that correction is done in situ on the telescope in the lenses. Okay, so as I said, I keep coming back to mass and saying, oh, look, the mass of the object is what determines how much deflection. So you can see where I'm going, right? If I want to tell you how much dark matter there is, or that there is dark matter, the evidence is going to be the deflections we see in the universe. So I'm hoping to now show you some beautiful pictures of deflections. But before we move on, I just thought one of you might end up asking me this question, is that it's the precise configuration of the lens, us, and the object from which the light is coming that gives you the range of phenomena that I'm going to show you. The many sets of multiple images. Sometimes, when things are just so, you can end up seeing something that's called an Einstein ring. You can end up seeing an individual distant object, which is actually a point source, stretched out, its light stretched out into a complete ring. And you might say, that's strange. Would we see that? Before I start showing you pictures, let me show you that this game, as I said, of trying to map what is the mass that's causing the light deflection can be done on different scales. It can be done with us and the sun and a star behind. It can be done and has been very successfully done by an experiment that has looked to see how much dark matter our own galaxy might have, right? So if we're sitting here, we're sitting right here, this is the center of our galaxy. Now, if we had a huge dark matter halo, what do we have to do? We have to look at some stars that are far enough away that we can actually see them, get the light from them, and then see if you have, say, dark matter with these kind of blobs, then these blobs would cause deflections, and all we have to do is measure those deflections, right? And say, okay, how big is our dark matter halo? So yes, there have been many experiments that have done that, and there are some very interesting results. But what I want to now show you is how we've just moved on to looking at these deflections in the universe that are telling us where the dark matter in the universe is. So this is that special case that I showed you, that once in a while, when things line up just so, you have the Einstein ring, which is the image of a galaxy that has been stretched. So there are actually two images, but it's been stretched to form what looks like almost a complete ring. And of course, it's called the Einstein ring because Einstein calculated that this should happen very rarely, but it should. It happens very rarely. But this is the first one that was observed. So in this case, the object that is lensed is a quasar, okay? And the mass that is lensing it is a galaxy. It's a galaxy between us and the quasars, okay? And this, the fact that you have these two images and you have it stretched out like this, allows you to figure out how much mass this galaxy has to have in order to accomplish this. And when we do that, you get a number, and that is 10 times to 50 times more than all the starlight that you see in this galaxy. You can add up the mass from the starlight. You can add up the mass of all the stars in that galaxy, and you find that the mass that you need for it to accomplish this lensing is 10 to 50 times more than what you see. So, and this is not the only case. As I said, this is a rare event, but there are many more common events where you find incontrovertible evidence for large amounts of dark matter. Yeah?
Does the calculation of the light that you're adding up for that galaxy, does that include possible planets that aren't giving off light?
Sure, it includes, it's very sophisticated what people do. They calculate this quantity called mass to light ratio, which depends on the age of the star, the mass of the star, how big the star is. And you know that stars form with different masses, and there's an aggregate of them. So all of that is taken into account, absolutely. And it's also taken into account that some stars will not shine invisible, they will shine in the infrared, and so on and so forth. So all of that's taken into account. And you still find that you need a large amount of dark matter. You might say, hey, she's shown us a one-off, right? No, in fact, it happens quite a lot in the universe. But you get different configurations each time. You don't get the same because the distance between us and the lens and so on is different. So you get very different phenomena. But here you get 4 images of the same object, and this is the lensing galaxy. You get an arc sometimes. You get a highly distorted arc. Okay, and you get just one. You get one very magnified, brightened one. You get one dimmed one. You get 2 images. You get a whole range of images. Okay, and from these images, we are able to map how much mass you really need. But let me just move on before I finish up to the grandest scale on which we are seeing this light deflection and what that's telling us about the dark matter in the universe. Okay. So, and in fact, I want to point out that this is sort of my particular area of research, which is trying to look at the distribution of dark matter. In fact, trying to map all the little clumps, okay, the details of all the little clumps. And the reason why, mapping all those little clumps is interesting and important is because just how clumpy things are might tell you something about the nature of dark matter. Remember, we know nothing about it so far. So that's really, this is sort of one of the sort of hot problems in the field of cosmology today, which is trying to get ways of mapping the dark matter, getting how many clumps there are, how they're distributed, to see if we can eventually kind of narrow down on the nature of dark matter, figure out what it's made of. So anyway, clusters of galaxies. This is an image of a cluster. A cluster of galaxies, in fact, is mostly dark matter, as we will see in a minute. Just from the amount of light deflection you see in it, you can tell, because you can once again add up all the starlight, and it's not enough. They act as gravitational lenses or telescopes, because remember, a telescope basically has a lens, right? It's focusing the light. That's what a telescope does. And what all these wonderful objects in the universe are doing for us are acting as telescopes. They're acting as lenses, as light collecting areas, right? And what is very interesting is that they also offer you a very interesting and powerful window in the universe. One of the things that the effect of lensing is that it also magnifies the object. Exactly what a lens, that's why we have used the word lens. It actually magnifies the object. So I want to end by showing you the image of the farthest galaxy ever found in the universe. And it was found behind a lens. And the only reason we found it is because it happened to be behind the lens. It's so faint, we would not have found it with current technology. Okay? So that's another incredible thing about this effect. Aside from the fact that we are mapping, the presence of vast amounts of dark matter make these objects very good lenses. And so they're magnifying things that are really faint that are behind them for us, which we would otherwise not see at all. Okay? So let me just tell you what a cluster is. Oh, this is just a few more images. And one more thing I wanted to mention to you is this light bending is independent of the wavelength in which you see the image. So you can see it in the radio. This is all in radio wavelengths. This is looking at a map, looking at these quasars in the radio, and you see all these multiple images. You see it in the visible, you see it in the X-ray, you see it in the radio. Okay, so this is, and the interesting thing is it's achromatic. It doesn't depend on the wavelength of the light that's emitted by the object. Okay, so what's a cluster? So the composition of a cluster that we know at the moment is about 1% of the mass is in galaxies, in stars and galaxies. 10% of the mass is in hot gas. That's kind of held together by the gravity of the cluster. The rest is all dark matter. So these are very, very interesting objects if we want to look at gravitational light deflections, because these are going to be the most efficient lenses for us. Of course, our questions are, how much mass, how much of that is dark, and how is it distributed? So this is just to show you a little animation of what happens when you have a screen of galaxies that are behind a cluster, which is very massive, which has a lot of galaxies. And this just shows you the range of, depending on each of these frames is slightly different because I've moved things around a little bit, okay, to show you that you see a whole range of deflections. Okay, so this is telling you that basically a galaxy will be spread out and will be torn into this arc, will be magnified. So this is the image you would see. So I want you to hold this, okay? This is a simulation, okay? Now I'll be showing you real clusters. And I bet you all of you will be able to pick up the images. That's how dramatic it is. Now that you know roughly what these multiple images, so right around the center of the cluster, you see these many multiple images in this, as you see in this animation. So let me just show you very quickly. You can see immediately. Okay, have we seen something like this before? Yeah. This is, in fact, a very, very nice lensed arc. It's an individual galaxy that has been stretched out. And once again, I'm telling you the story now, post facto, when observations, people admitted right away, and they did the calculations and said, it is lensing. But it wasn't that easy. This object was seen It was considered to be a very mysterious giant arc, and they hadn't figured out that this was probably a lensed image. And this was in the 70s, and this is the close-up of a cluster in the central regions of a cluster. And this is another one, and this is a very dramatic one. I'll show you another picture of it, a Hubble Space Telescope picture. So already, once people had accepted that this could be gravitational lensing, they started doing the mass inventory, and they said, gosh, the clusters are much more massive, because they were able to catch how much dark matter there was in the clusters. And remember, the bulk is. So this is one of the best studied gravitational lenses in the universe. This is a cluster of galaxies. And everyone can see the distorted images, right? See them here, here, see all the arcs, see the arcs around here. So in this particular field of frame that we're seeing, there are 17 sets of multiple images. Okay, that gives you a really good handle on the distribution of mass and of matter in this region of space. Okay? And this is another one. So these are all Hubble Space Telescope images. So you can see here, 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 you can see all the arcs. And you can probably tell right away, just from the number that you see here, that this cluster is probably not as massive as the previous one we saw. And you would be right. So let me show you a couple more, and I'll show you a little bit of a close-up. And show you sort of roughly what cosmologists study. What about these images do we study? So this is that image that I just showed you. So what we work on is try and model this arc. This is the arc, and I've removed all the other stuff just to close in on the arc. And what you do is you solve the equations, and you put in the amount of mass that is needed, and you have to match what is observed. You have to match the length of this arc, the curvature of this arc, the shape of this arc, as well as the detailed distribution of the light along this arc. That's what we do in the modeling. And that's what tells you how much mass, and that is determined by how much dark matter basically you have and how it's distributed. So it's a very, very nice, fun mathematical problem, which is very well constrained, solvable. So this is actually my favorite cluster. It has 5 sets of multiple images of the same galaxy. The interesting thing is that this galaxy that is multiply imaged is a very interesting galaxy in itself. It's actually it's a ring galaxy, shaped like a little cartwheel. And isn't that amazing? You see the same structure in all the 5 images. And remember, I told you that we already know by looking at the spectra of all of these that they're, in fact, they're confirmed that they're all multiple images of the same galaxy. So this is another of the current clusters. So this, I just wanted to show you one slide of my work so that you have an idea of what it is that I actually do. So what I do, what you see here is an image from the Hubble Space Telescope that are sort of these dark patches. Those are the galaxies in the cluster. And what you see here is my model for the dark matter. And what you see are these circles are the halos of dark matter around these individual galaxies that you need to have in order to produce the lensing that is seen. Okay? And so this is the kind of work that is done. So now this is the kind of detailed map that we have. So now we know that the dark matter is kind of blobby. There are these blobs. These little red circles tell you how big the dark matter halos are. And we know there are quite a lot of blobs. It's sort of very blobby. So now what we're all working on is try and figure out what the implications are. If the dark matter is so blobby, what could it be made of? If we know that it has to be so blobby and not smooth, right? It's not smooth. It's actually very, very blobby. I think I have just 2 more slides before I wrap up. This is, as I was putting things together for you all yesterday, I got an email from Space Telescope Science Institute saying, hey, we discovered this new funky lens. What do you think? And I said, oh, gosh, I have to show this. So this is not cleaned up, et cetera, yet, but this is fresh off the telescope. So this is a lens that was discovered last week. It's a cluster of galaxies, which is, in fact, very far away from us. It's farther than all the other clusters that I've shown you. So when you think about the configuration, the lens is very far from us, and the source is even further behind. Right? Yeah.
How far back in time are we looking?
We're looking back to a time when the universe was 15% of its current age. That's how far back we're looking. That's a very good question. Should have mentioned that. Okay, so this is just a zoom in of that galaxy that I showed you in the lens. And this is my last slide. Remember I told you that one of the other things that the lenses can help you do is to, by chance, allow you to see some very faint objects that you would not otherwise see because you magnify the light. And so what has been the highest redshift galaxy that has been conclusively imaged and discovered is one where discovered at a redshift, which is quite far away. It is at a distance from us where we could not have directly imaged it if it didn't happen to be sitting behind this lens. We just wouldn't have discovered it with current technology. Maybe in 10 years' time we would, but at the moment we wouldn't have. Okay, so this is the youngest object, if you will, in the universe, the earliest sort of galaxy that formed that we have direct light from at the moment. So, yep.
This may be a little bit off the subject, but something I'm rather curious about. Has there been done to say whether or not there's a speed at which gravity acts? I mean, we talk about light acting at a speed that gravity
Yes.
acts.
Yeah, absolutely. There has been a lot of research, and there are a lot of models on trying to characterize what might be a relevant time scale and spatial scale over which gravity. So there are these theories called modified Newtonian dynamics, which deal with that, and we can talk a little bit if you want to know a little bit about what's done at the moment. They are considered slightly speculative theories at the moment because they don't actually fit in comfortably with all the data that is seen. One can argue that it fits with some pieces of data, but not with others.
So basically, we're not sure at this point if gravity acts at a speed at a distance.
Well, it doesn't appear to be a finite speed at the moment.
It does not.
No, there's no evidence. But there are people who are working on models. Yeah.
Could you give us an idea or approach to how dark matter behaves dynamically? Follow the same. You mentioned universality.
That's a very nice question. Yeah.
We have evidence to show that it behaves with the same laws, or in effect with dark matter and dark energy, or is there more of a randomness to it?
No, it's a very good question. The question is, what are the dynamical properties of dark matter? We understand quite a lot about that, and it appears that dark matter just behaves only via gravity. So you can start off only via gravity. They interact only via gravity, and the entire dynamics and evolution is determined only by gravity. And the way we know that is because we have these very large computational simulations in which we can start off with an initial sort of universe, conditioned universe. Because remember, we know that the dark matter dominates the universe. So you can start off with a lot of particles of dark matter, let them go, let them evolve with time, and see if they would cluster into these halos. And in fact, they do. They cluster very well into these halos. So just gravity seems to do the trick in describing all the dynamics of dark matter.
So why don't we thank our speaker, and those who have questions can come and approach her later.